Hello everybody, this is Dr. Christopher White and today we are moving on to lecture number 19, during which we are going to be looking at the Cenozoic Earth History, or at least the second half of it. So we're going to be focusing on the Quaternary. Alright, so the Quaternary Period. So the Quaternary Period extends from around 2.6 million years ago to the present day. It consists of two epochs. The first epoch is the Pleistocene, and that goes from around 2.6 million years ago to around 12,000 years ago. Now, the Pleistocene is defined by what's referred to as an icehouse period. So during this period, we had several large-scale glacial events, mostly focused in the northern hemisphere. After 12,000 years ago, we shift from the Pleistocene into the Holocene, and the change from the Pleistocene into the Holocene is marked by the retreat of the final large-scale glacial event, which of course we refer to as the last ice age. And so once we see this large-scale glacial event beginning to retreat, and obviously we begin to see the effects of that retreat in the environment, we can say we've shifted from the Pleistocene into the Holocene. Now, the Holocene itself is, well, at least it was, should I say, was not actually split up into ages. It was just a chunk of time, around 12,000 years in size. So this led some geologists to decide that, well, there needed to be some kind of internal segregation of the Holocene, and so a decision was made that by a group of geologists they were going to work together to try and define a new age within the Holocene, which was going to be referred to as the Anthropocene, or should I say, they would come up with a new age within the Holocene, which would be referred to as the Anthropocene, or they would come up with an entirely new epoch, which would be called the Anthropocene, and the Anthropocene would obviously follow the Holocene. Now, obviously, the problem with that is any boundary in the geologic timescale has to be defined by some kind of significant change, which is measurable within rocks and fossils. So, obviously, that's a very, very difficult thing to do. And so it led to a lot of discussion, and three possibilities were put forward to allow us to essentially define a boundary between the Holocene and the Anthropocene, or at least define the boundary of the Anthropocene if we decided to use it as an age within the Holocene. And so the possible options to define these boundaries were, of course, the Industrial Revolution. So that's around 250 years ago, so relatively recent. But of course, the Industrial Revolution is going to mark a period of very significant environmental change. We're going to see things like increases in the amount of carbon dioxide in the atmosphere. We're going to see increases in the amount of sulfur in the atmosphere, and we're going to see a very rapid retreat in the amount of woodland, essentially as large-scale industrial farming begins to become more common. And we're also going to see a lot of extinction events from the Industrial Revolution onwards, because obviously we're going to have a very significant effect on the environment, and that's going to lead to lots of animals becoming extinct. So that was one of the possibilities. The next possibility was just simply referred to as antiquity, and that says around 2,000 years ago we begin to see the flourishing of several very major civilizations simultaneously. And so the argument is that the flourishing of these very large civilizations would have had obviously a very significant effect on the environments in which they were operating. And obviously, once again, that makes sense. Large-scale civilization requires significant quantities of food, so that means very, very large-scale farming. That means large scales of deforestation. That means large amounts of extinction events in a very small area. And so some people suggested, right, antiquity would make a very reasonable marker for the start of the Anthropocene. And then the final option was the appearance of farming. And so when it comes to the appearance of farming, we can actually mark that out by looking at the spores, which we see contained within sediments. So we can look in the sediments, we can look at the spores, and we can see around 8,000 years ago, there's a shift. We suddenly see large numbers of spores associated with cereal crops, like wheat and barley and malt, suddenly begin to make an appearance. And so what this means is we have the first stages of large-scale farming going on. And so once again, by using the spores contained within the sediments, some scientists suggested that we could use that to define either a new age or a new epoch, which we would obviously label the Anthropocene. So, and at the moment there's a group of scientists who are currently trying to work out exactly what the best boundary for the Anthropocene would be. But in July of 2018, something rather unexpected happened. So over on the right here, we actually have the section for the Cenozoic of the International Chronostratigraphic Sequence, and you can see up here. Here's the Holocene, and you can see the Holocene has been split into the Greenlandian, the North Grippian, and the excuse my pronunciation. The Megalhelian, and this came as somewhat of a surprise because people hadn't actually quite realised that the IUGS were going to do this, and so it's led to a lot of infighting within the geologic community. So, there was a very significant change there. So these ages within the Holocene are defined by the following. So the Greenlandian is obviously marked by the end of the last ice age, and the North Grippian is marked by a large quantity of glacial melting, which led to an increase in fresh water entering the oceans, and that led to the disruption of ocean circulation. And we can see that in the geologic records. That's when the North Grippian starts. So North Grippian starts around 8,000 years ago, goes through to about 4,000 years ago, and around 4,000 years ago we move into the Megalhelian, and that's when we see a very significant change in global climate, which leads to a very noticeable period of drought. And this period of drought led to several major civilizations being put under great stress, and it also led to the collapse of several ancient civilizations as well. So, we can see that within both the geologic and the archaeological record. And so this caught everyone by surprise, I think it's fair to say. People weren't expecting this, and so yes, so this is the new breakdown for the Holocene, and it's led to a lot of argument, and there are a lot of very angry geologists out there, because a lot of geologists feel that the Anthropocene should have been either an age within the Holocene or an entirely new epoch altogether, but the IUGS kind of jumped ahead of them and decided to split it up into these three ages here. So there you go, a little bit of geological politics there for you. Okay, so the transition from the Pliocene to the Holocene occurs around 12,000 years ago, and it's defined by the start of warmer conditions associated with the melting of the most recent continental glaciers. That's the period we refer to as the Ice Age. So essentially 12,000 years ago, we see the start of the last Ice Age ending. So we see this change from this ice age, icehouse conditions to essentially higher temperature conditions being marked out by the deposition of till layers. So if you remember, till is the very poorly sorted sedimentary rock that's deposited by glaciers. And so the sediment that makes the till is held within the ice of the glacier. And obviously as the glacier melts, the sediment is deposited and released, and that makes the till. So obviously what happens is, when you have large-scale glacial melting, you have large quantities of till being deposited. And we can see around 12,000 years ago, we start seeing the deposition of very substantial quantities of till, and that suggests there's a lot of melting going on. Another thing that we see happen is we see a movement of temperate regions northward. So a temperate region is essentially the kind of region that we're in now. Relatively warm, comfortable summers, and cold winters. And essentially, so we have cooler, so we have cooler winters and autumns, and we have warmer springs and summers. So we have these defined seasons. Well, which obviously you won't get in an equatorial region. In an equatorial region, the seasons are on the whole relatively similar. So winter is pretty close to summer. So what we see with the temperate regions is we see that during the last ice age, because the ice moved south, so the very northern portion of the northern hemisphere obviously became very, very cold. Well, that pushed the temperate regions, which were, which in their current position cover most of Canada and the United States. Those were pushed south towards the southern United States and Mexico. So that meant that the modern temperate conditions were pushed over the southern states and Mexico. And obviously what happens is as the ice begins to retreat and moves back northwards, this temperate band begins to move from the southern states and Mexico northwards as the ice retreats. So we begin to see the shift of the temperate bands away from the equatorial regions and into higher latitudes. Obviously, as we begin to see the changes in the conditions caused by the retreat of the ice, we're going to see changes in vegetation. So during the last ice age, because the temperate band was pushed further south, it meant that the southern states of the United States were essentially quite, well, relatively comfortable and relatively wet. And so this meant that obviously there was large amounts of vegetation in the area, huge forests. And so what we see at the end of the Pliocene going into the Holocene, we see these temperate bands begin to move north, and the temperate bands for the southern states of the US, Texas is a great example of this, we begin to see the climate shifting from a relatively wet climate to a much drier climate. And this leads essentially to the collapse of these forest ecosystems, and so we see very substantial changes in the fossilized vegetation and also the pollen, because we see new plants coming in, replacing the old plants, and we can see that in the change in the pollen as well. And the final thing we see is a change in the oxygen isotope ratio of marine shelly organisms. So we can look at the calcium carbonate that makes up the shells of things like oysters, for instance, and we can see based on the oxygen isotope data that something is changing. And so obviously the question is, well, what do we see? Now we are going to go into this in greater detail later on, so this is going to be a very quick skirting over exactly what we see. So what happens is glacial ice locks up large quantities of what an isotope called oxygen-16. Now, oxygen-16 is by far and away the most dominant isotope of oxygen. So, it makes up a very substantial portion of all the oxygen out there. So there's lots of it in seawater. Now, what happens is during periods where we have large-scale glacial events, a lot of that oxygen-16, which would be in the seawater, gets locked up in ice. So that means it can't get back to the oceans. So typically, water evaporates from the oceans, it falls as rainfall, enters a river, and that river dumps the water back into the ocean. So you have a constant cycling of the oxygen-16. In the case of a glacier, water goes into the atmosphere, falls as snow, that snow gets compacted to make ice, and the water is now trapped in the ice. It's not going back into the oceans. So during large glacial events, what we see is we see lots and lots of oxygen-16 getting locked up in the glacial ice. And so we see the amount of oxygen-16 in the oceans dropping slightly. And this is reflected in the amount of oxygen-16 that we see within the calcium carbonate of shelly organisms like oysters. And so we can measure this. And so what we see is around 12,000 years ago, we begin to see the amount of oxygen-16 increasing. And so this tells us that glacial ice is melting, that's releasing the water, and obviously the water contains lots of oxygen-16, that's releasing that water back into the oceans, and so the amount of oxygen-16 in the oceans starts going back up, and we can measure that in the calcium carbonate of the shells of, as I say, animals like oysters. So these are the four changes that we look for to define the transition from the Pleistocene to the Holocene. So the Pleistocene is often referred to as the Ice Age, and during this period we have extensive ice sheet coverage, mostly focused in the northern hemisphere, mostly focused in North America, Europe and northeastern Asia, down to about a latitude of 45 degrees. So the Pleistocene is marked by extensive till deposits. That's to be expected because we have large-scale glaciation, which means obviously large amounts of glacial sediments being produced. We also see lots of polished and striated bedrock. So if you remember, as a glacier moves through an area, it will strip off the topsoil and the glacier will end up resting on the rock that's underneath the soil, which we refer to as the bedrock. So the glacier will move across the bedrock, and all the very, very fine pieces of rock that are trapped at the bottom of the glacial ice, well, they'll rub against the bedrock as the glacier moves over it. And that means that the very, very fine pieces of rock will actually polish the bedrock, and that leads to what we refer to as a glacially polished or glacially smoothed bedrock. Now, within that bedrock, we will also see very, very large lines, which are referred to as striations. And striations are caused as the glacial ice moves over the bedrock. Within that glacial ice, there will not only be small pieces of rock, there will also be large pieces of rock. We're talking, boulders, cobble, gravel-sized clasts. So as one of those gets dragged across the glacial ice, across the bedrock, it's obviously going to cut a really deep groove as it goes in the bedrock. And so we see lots of glacial deposits, we see lots of polished and striated bedrock, and the other thing we see are lots and lots of U-shaped valleys. So a U-shaped valley is produced by a valley glacier. They tend to form in mountains. And a valley glacier will produce a valley that has a very distinct morphology to it. Essentially, it looks like a U. So glaciers and ice sheets are moving bodies that move by one of two methods. So the ice in a glacier will move in one of two ways. It can move by plastic flow, in which that's when the ice deforms in response to pressure. So essentially you're putting weight on the ice, and so the ice will naturally flow. And the other option is basal slip, and that's simply when the ice slides over the underlying surface. So let's actually quickly have a look at the three main types of glacier that there are. So the first type of glacier are called valley glaciers. Now these are commonly found in mountainous areas, and they are limited to, as the name suggests, valleys. So there's high ground on one side, high ground on the other side, and the ice, essentially the river of ice, the glacier, will flow between those two regions of high ground, essentially in the valley between them. So valley glaciers are like rivers, so they're very long and they're very narrow, and they're confined by the topography. Okay, the high ground either side stops the valley glacier from spreading out over a larger area. So just like a river, a valley glacier will start at an area of high topography, and it will flow under gravity down to a lower point in the topography. So it will move with gravity. So in the case of valley glaciers will move by both plastic flow and basal slip. Okay. Now the reason that they can move by both, basal slip's obviously quite straightforward. The ice is simply moving over the ground. In the case of plastic flow, because valley glaciers are smaller compared to the other two types of glaciers, they don't have as much weight, and so that means they can very often move in a plastic fashion. Now, the other two types of glacier are continental glaciers and ice caps. So in the case of continental glaciers, they will cover an area of at least 50,000 square kilometers, and they're unconfined by topography. They go wherever they want. So a continental glacier will obviously start flowing out from a central point. That's where the glacier starts, and the ice will go in all directions from that central point. Now, in the case of a continental glacier, because it's so big and so heavy, it will primarily move by plastic flow. Okay, so in the case of a valley glacier, because it's relatively light in comparison, the ice can actually slide over the bedrock below. In the case of a continental glacier, because it's so big and heavy, it will naturally grind into the bedrock. It will push down on it. The amount of friction between the ice and the bedrock will be very, very high. And so that makes basal slip considerably more difficult. It happens, but it's not as easy. So in the case of continental glaciers, most of the movement of the ice is accommodated by plastic deformation. Now, the other type of glacier we have is ice caps, and they're the same as continental glaciers, but they have an area of less than 50,000 square kilometers. So when we think of areas of the Earth that are covered by large quantities of ice, well, there are two areas of the Earth which are essentially continental glaciers. There's obviously Antarctica and Greenland. So in both these areas, we have large areas in excess of 50,000 square kilometers covered by glacial ice. So you might be thinking, hold on, what about the Arctic? Well, the Arctic doesn't actually classify as glacial ice. It's technically sea ice. So in order to be glacial ice, the ice has to be sitting on solid rock, has to be sitting on continental crust. Now, it's very, very common for people to refer to Antarctica and Greenland as being covered by ice caps. They're not. If we're being strictly scientific about it, they are in fact covered by continental glaciers. So once again, valley glaciers, smaller. Because they're smaller, they'll move by both plastic flow and basal slip. In the case of continental glaciers, they are unconstrained. They can go wherever they want. They're often much bigger, much heavier, and so most of the flow that occurs with the ice is produced by plastic deformation of the ice, with a very minor component of basal slip. So during the Pliocene, there were several episodes of glaciation. So it wasn't just one big glacial event. So these episodes of glaciation are separated by what we refer to as interglacial intervals. So these are periods when the Earth's climate actually warmed up a little bit. So you'll see the glacier expand during a glacial event, and then you'll see in the interglacial the global climate will get a little warmer for a while, and you'll see the glaciers begin to retreat a little bit. Then the interglacial will finish and the glaciers will advance again. So at their maximum extent, the ice caps during the Pliocene covered no more than 30% of the Earth's continental surface, mostly in the northern hemisphere. So, as I said, a large proportion of North America, mostly Canada and the northern states, a very large portion of Europe, essentially Scandinavia, coming all the way down to Denmark, northern Germany, Scotland, and very northern England, northern Wales. That area was covered by ice. And then we have essentially northern Russia was also covered by ice during the last ice age. Now, this large-scale glacial event will have led to temperatures being approximately 4 to 7%, so let's try again, 4 to 7 Celsius lower than present day. And this is a reflection of several factors. Some of them will come to at the end. But obviously one of the main factors is the more glacial ice you have, well, obviously glacial ice is very, very light. It reflects sunlight and therefore solar radiation and therefore heat back into space. So that means the Earth will be cooler the more glacial ice you have. So obviously when we have 30% of the ice covered in 30% of the Earth covered in glacial ice, that means more solar radiation gets reflected back into space. Therefore, the Earth's global temperature will decrease. So, as we already touched on, these lower temperatures will cause the temperate region, which we live in now, to migrate southwards. And so this meant that during the last ice age, areas like the Sahara and the southern United States, which are on the whole relatively dry, were actually quite wet. And so, as you know, it means, for instance, during the last ice age, the Sahara was a very heavily forested area. So it's actually uncertain whether we have moved out of the most recent ice age. Some scientists actually believe that at the moment we are actually sitting in an interglacial interval, and there's a good chance that a new stage of glaciation might actually start at some point. But you know, on the whole, most scientists think we've actually left, you know, the most recent ice house period, and now we're into a period of global warming. Okay, so let's have a quick think about Quaternary tectonism and volcanism. So during the Quaternary, plate tectonics and volcanism were very similar to the present day. Essentially, if it's happening now, it was pretty much happening in exactly the same way during the Quaternary. So we had the Alpine Himalayan and the Circum-Pacific orogenic belts doing their thing, and we had the rates of convergence of the continental plates, so the rate at which tectonic plates were heading towards each other or moving away from each other or moving past each other, were relatively similar. So everything was happening in pretty much the same way at pretty much the same rate. So we see on the western seaboard of the United States, we see stresses caused by the movement of the Pacific plate past the North American plate along the San Andreas fault zone, led to significant faulting and folding in the west and southwestern United States. That's still going on now. And this produced several small basins and uplifted areas. So remember, a basin is essentially a topographic low, which will fill with water eventually. So this deformation produced several small basins and uplifted some areas. And this uplift is reflected in the large quantities of sediment being deposited on the Pacific continental shelf. So all this deformation produced some areas of high ground. Obviously, as we've touched on several times in the past, areas of high ground will naturally experience high rates of erosion, producing large quantities of sediment, which is deposited along the Pacific coast. In terms of what's happening within the central United States and the eastern United States and the Gulf Coast region, it was pretty much exactly as it is now. Nothing interesting to report there. So what about volcanism? So volcanism continued on the west coast, but it became limited to the Cascade Range. So that's a region from northern California through Oregon, Washington State, and into the southern half of British Columbia in Canada. So this region essentially has several volcanoes. Of course, some of them you might know. Mount Rainier, Mount Hood, Mount St. Helens are ones you've probably heard of. And the volcanism in this region became more pronounced in the Quaternary, forming several large composite volcanoes and lava domes. So what we actually noticed within the last 2.6 million years, we've actually seen a bit of an increase in the amount of volcanism associated in the Cascade region. So we also see sporadic volcanism, representing the latter stages of volcanism seen in the Paleogene and Neogene, and that also took place in Arizona, Idaho, and California. So, if you remember, within the Paleogene and Neogene, we obviously had the effects of this very large mantle plume that got stuck under the Farallon oceanic crust, which was subducting underneath North America, and eventually that mantle plume managed to burn its way through the Farallon oceanic crust, and it sat at the bottom of underneath North America, and of course that led to relatively large-scale volcanic events during the Paleogene and Neogene within the western states of the USA. We see that volcanism beginning to decrease as you head into the Quaternary, and as we've been moving further and further into the Quaternary, that volcanism has on the whole nearly completely disappeared. So, for instance, when you think of Arizona, when you think of Idaho, you don't really think of volcanoes. And there's a reason for that, because the volcanism has on the whole stopped. So we see substantial eruptions in the Yellowstone area at 2 million years ago, 1.3 million years ago, 0.6 million years ago. And each one of these produced a large caldera measuring about 76 to about 45 kilometers in diameter. And the calderas are partially filled with a mixture of tuff, so pyroclastic volcanic rocks, and the most recent caldera is filled with a sequence of tuffs that date from about 150,000 to 75,000 years ago. And so if we actually look at this diagram here, of course that would really help, but we can't see it very well. We can actually see we have several coloured circles here coming this way. Over here we have the modern day position of the Yellowstone caldera. Okay, so that's where the modern Yellowstone National Park is, and where we have geysers like Old Faithful. And so what we have in this area is we have a caldera type volcano. So obviously, if you remember, a caldera is when we have a large circular depression on the Earth's surface, within which we often have several smaller volcanoes. And underneath the caldera we have a magma chamber. In the case of Yellowstone, that magma chamber is actually currently filling up because we can see the ground beginning to rise slightly. And so there is a chance that there could be a very large volcanic eruption within the Yellowstone region within our lifetime. And we can actually see several of these large eruptions, essentially ranging from around 2 million years ago over here, to around 0.6 million years ago over here. In fact, these volcanic eruptions go all the way back over here to around 15-16 million years ago. And this chain of volcanic events here shows us that North America is moving in a approximately westerly direction over a hotspot which is trapped underneath North America, and that hotspot is probably associated with the mantle plume that got stuck underneath the Farallon plate during the Paleogene and Neogene. Obviously, that led to the Laramide orogeny. So, on the whole, we see volcanism up here in the Cascade region. We see a little bit of volcanism over here associated with this mantle plume. And then that is pretty much it in terms of volcanism in North America during the Quaternary. Okay, So let's have a think about the stratigraphy that we see during the Quaternary. Oh, do you know what? I've suddenly realised I've gone way past my normal stopping point. So let's pause here. So pause the presentation, get up, have a walk around, and please come back in a few minutes. So, as already mentioned, the Pleistocene marks a period of very, very large-scale glaciation, and so we're going to see this reflected within the sediments that we see deposited during the Pleistocene, and obviously therefore the rocks that form from those sediments. So what we see in the Pleistocene is we see lots of glacial deposits, so lots of moraines, what we refer to as erratics. Those are very, very large boulders that are dumped by glaciers as the ice melts. And obviously we see lots of these polished and striated bedrocks associated with the movement of the glaciers. And from what we've been by looking at these moraines, the erratics and the striations, we've been able to determine that the glacial maximum during the Pleistocene covered 3 times more of the Earth's surface than at present. So approximately 45,000 square kilometers, give or take a bit. Oh, sorry, should I say? Yeah, don't worry. So, and that ice had a maximum depth of around 3 kilometers. So, in North America, mapping of glacial deposits has revealed several glacial stages. So once again, as we already touched on, an icehouse period isn't marked by a single, event. So the glaciers don't just start growing, reach their maximum size, and sit there. The glaciers will grow for a bit. Then there'll be one of these interglacial intervals where things will warm up, the glaciers will retreat a little bit. Then things will cool down again, the glaciers will advance a little bit. There'll be another interglacial, the glaciers will retreat a little bit. Then we'll see the glaciers advance again, and so on. And this will happen several times during one of these icehouse periods. So what we can do as geologists is we can look at the glacial sediments, and we can actually look for these interglacial intervals, these periods of essentially warming up where we see the glaciers retreating, and then obviously the advance that follows that retreat. So as the mapping of glacial deposits has become more refined, initially we could only find 4 glacial stages, and over time we've actually managed to work out, based on the observations of sediments from land, that there are 11 stages, and these 11 stages are termed pre-Illinoisian A through K. So here we go. So if we look, here's the Pleistocene, we've got the Holocene up here. So during the Pliocene, you can see here it starts around 2.6 million years ago. We have pre-Illinoisian K down here, J, I, H, G, F, E, D, C, B, and A. And so these are the events that we've been able to pick out by looking at the glacial sediments. So what happens is these are all periods of glacial advance, and they're all going to be separated by one of these periods of warming, which obviously refer to as a interglacial. So analysis from other areas revealed similar stages, but the number and terminology will vary. And this is due to the very chaotic nature of glacial deposits and the erosive effects of subsequent glaciers. So the problem is number one, if I look at the sequence of glacial sediments, let's say in Michigan, and I compare that to the glacial sediments that I see in, let's say, North Dakota, I'm going to get a very significant difference in what I see. I'm not going to be able to see the same stages in Michigan that I would see in North Dakota and vice versa. And that's because glaciers are naturally very, very chaotic things. So if you imagine a situation where we have a glacier, it's advancing, it's depositing sediment as it goes, then it begins to retreat for a little while in one of these interglacials, and during that retreat it deposits even more sediment because the ice is melting. Well, in some areas, that sediment that's being deposited during the interglacial will be preserved, and we'll be able to see that, and as geologists we'll be able to say, right, there was an interglacial right there. However, in some areas, what will happen is when the glacier starts advancing, it will just plough through that sediment that was deposited during the interglacial, and it will just obliterate it. And so we would never know that interglacial was there. And so it's very difficult to find all of these stages in every location. The stages you can find in each location will vary. Sometimes you can find all 11 of them, sometimes you can find one. So it's very difficult to correlate between areas. So for instance, if I'm in North Dakota and I can just work, I can just find one of these stages, well, the problem is am I looking at pre-Illinoisian K, or am I looking at pre-Illinoisian E or A, for instance? I don't know. So it's very, very difficult to tie up glacial events, even over relatively small distances. So it's very difficult to do that over local scales. Imagine trying to do that globally. So people have actually tried to tie together glacial events in North America to glacial events occurring in Northern Europe. And the attempts that have been made to do that have met with massive failure. Because once again, it's just so chaotic. It's very difficult. You can't say, right, I can quite easily see, these sediments associated with pre-Illinoisian G, over here, near Stockholm. You can't do that because there's just such variation between the two locations that it's impossible to do that. Now, based on what we've seen on land, as I say, we find these approximately 11 stages, which we refer to pre-Illinoisian A through K. Now, more recent work has actually picked out a few more. We have the Illinoisian. We have the, now, once again, excuse my terrible pronunciation. Here we go. Sangamonian. And we have the Wisconsinian. They were added a little bit later. Now, what's happened is we've actually managed to get hold of deep ocean cores. These deep ocean cores are produced as part of the oil drilling industry. So obviously when oil companies drill, they're obviously drilling down to the rocks, to try and get hold of oil and gas. The sediments that are sitting on top of those rocks, they don't care about them. They're in the way. So it's it's not uncommon for these oil companies to give these sediments to geologists to study. And so geologists will look at these sediments and what do we find? Well, when we look at these deep ocean drill cores, we can see that there were in fact 20 warm-cold cycles during the Pliocene. So on land we can see we've got these. Based on the sediments in the ocean, we can see there were in fact 20 of them in total. Now, this evidence is primarily based on the oxygen isotopes that we mentioned earlier. So if you remember, during periods where we have large-scale glaciations, we'll see the amount of oxygen-16 in the oceans decrease. During periods of glacial warming, so during periods of warming, when we see the glaciers retreating, we will see the amount of oxygen-16 in the oceans increase. So we can see that once again reflected in the carbonate that organisms are using to make their shells out of, and so all we have to do is measure the oxygen isotope ratios of those organisms that are contained within the deep ocean sediments. And so by looking at that data, we find that there were in fact 20 of these warming cooling cycles. So once again, that shows you during the Pliocene there were 20 of these events where the glaciers extended, retreated, extended, retreated, extended, retreated. So they did it several times. So it wasn't just one smooth process. So what's actually happening during the Pliocene what's happening during the Pliocene in the deep oceans? Well, as I mentioned, initial attempts up until the 1960s to constrain the number of Pleistocene glaciations were limited to terrestrial deposits because that's all we had access to. However, as the technology required for deep-sea drilling became available, the sediments that were being brought up as part of these deep-sea drilling programs, mostly from the oil industry, became available for study. As I said, the oil industry didn't care about them, they're not of any use to them, and so the oil industry would give these sediments to universities and professors to study. So we need to remember that these very, very deep ocean sediments have no erosion. Okay, so no material can be lost. All that happens is over time we have a very, very slow accumulation of material in these deep ocean sediments. And so this means that what we're seeing is definitely a complete sequence of sediments for the Pleistocene. So that's how we can be certain that during the Pleistocene there were 20 of these events, because we know no sediment could be eroded, and therefore no sediment has, we know with certainty that no sediment has been lost. So within these clays, these deep ocean sediments, we find the shells of microorganisms, especially an type of organism we refer to as foraminifera, which you'll be familiar with because we mentioned it several times before. And foraminifera live in the upper layers of the ocean's water, and of course when they die the carcass sinks to the bottom, the organic portion decomposes, but the shell of the foraminifera gets incorporated into these deep marine clays, and we can come along later, analyze these shells and get the oxygen isotope data from them. So foraminifera are useful because some species have very limited conditions of growth. So essentially for some species the temperature has to be just right. If it's too cold or too warm, they can't live in those environments. So we can use foraminifera to actually to infer changes in ocean surface water temperature based on 3 changes that we can see. The first one is the type of foraminifera. Is it a hot water foraminifera or is it a cold water foraminifera? That tells you what temperature the surface water was. Was the surface water cold or was it warm? The next thing we can do is look at the coil direction. How is the shell coiled up? And the final thing we can look for is we can analyze the calcium carbonate of the shell, and we can look and get the oxygen isotope ratio from that calcium carbonate. So let's look at the 3 pieces of information that we can get from these foraminifera. Obviously, as mentioned, the first one is temperature, in terms of what type of foraminifera do we have. So many foraminifera are temperature sensitive, and they will migrate to different latitudes as surface water temperature changes. And so, for instance, if we were, let's say, off the coast of, well, let's pick anywhere. Let's say we're in the area around New York, around, let's say, around 2.6 million years ago. So around that time, the climate in that area probably would have been relatively temperate, probably relatively similar to the climate that New York experiences now. And so what will happen around 2.6 million years ago is we'll see the climate will steadily get colder and colder and colder as the ice begins to move steadily south. And so what this means is the temperate conditions that exist around 2.6 million years ago are steadily pushed further south, and the climate will become colder and colder and colder. And so we can see that change in the foraminifera. We will see foraminifera that are stable in more temperate conditions will be replaced by foraminifera that are more stable in cold water conditions. So that's telling us that this, the temperate band is being pushed more towards the equator. And so a good example is during a period with a cooler global climate, we have a particular type of foraminifera called Globigerina, and that will be restricted to near equatorial conditions. So Globigerina actually likes relatively warm water, and so what we notice is during periods where we have large-scale glaciation, the area in which Globigerina can exist becomes restricted, because as obviously the temperate bands move towards the equator, it means the equatorial band begins to be compressed and the equatorial band gets smaller. And so there's less room for Globigerina to live. And obviously, as the global temperatures begin to increase again and the ice sheets retreat, we begin to see Globigerina begin to move up into higher latitudes. So we can just track this. We can track these changes in ocean temperature just by looking at the type of foraminifera we have. Is it a warm water species or is it a cold water species? The next thing we can look at is the direction of coil. So in response to water temperature changes, some foraminifera will actually change the direction in which their shell coils. So if we look at this foraminifera here, we can see the shell is coiling in a rather nice set spiral direction. Okay, so we can see how it's coiling there. Some species, when the temperature changes, the coil direction will change, and so you'll see the shell actually coil in the opposite direction. And so we can, as geologists, we can once again filter out the foraminifera fossils. We can look at the direction of coil of the shell, and we can say, right, well, this shell is coiling in this direction, therefore that means the water temperature has to have been approximately this, or this foraminifera shell is coiling in this direction, therefore the temperature has to have been somewhere in the region of this. So a good example is this Globigerina species with an absolutely horrible species name, which I'm not even going to try and pronounce. And this particular species will coil to the right in warmer waters, essentially in excess of 10 Celsius. However, if the water temperature drops below 8 to 10 Celsius, it will begin to coil to the left. And so, once again, just by a simple observation of the foraminifera, you can very quickly work out, what was the approximate range of the water temperature. Was it warmer or colder than 10 Celsius? The final thing we can do is we can actually analyze the calcium carbonate of the foraminifera shell, and that's going to allow us to get the oxygen isotope values. So if we look at the oxygen isotopes, we can see there are three main ones, 16, 17, and 18, and we can see that nearly all oxygen is oxygen 16, followed by oxygen 18, and oxygen 17 only makes up a very, very minor component of oxygen. We are interested in oxygen 16 and oxygen 18. So obviously water will contain both oxygen 16 and oxygen 18. Remember, water is H2O, 2 hydrogens, 1 oxygen. So some of those water molecules will have an oxygen 18 water molecule, and some of those will have an oxygen 18 isotope, and some of those water molecules will have an oxygen 16 isotope. And we know that the vast majority of water molecules will actually have an oxygen 16 isotope because it's by far and away the most common isotope of oxygen. So what does this mean? Well, oxygen 18 has 2 more neutrons than oxygen 16. That means it weighs ever so slightly more. Now, in terms of the difference in weight, it's absolutely tiny, but that difference in weight will actually have significant repercussions for how the water molecules behave. So the first thing the first thing that happens is the sunlight hits the oceans, and that's going to cause water from the oceans to evaporate into the atmosphere. That's the first stage. Now, amazingly, even because the oxygen 18 is just that little bit heavier, it is actually more difficult to make a water molecule of oxygen 18, make a water molecule containing oxygen 18 evaporate compared to a water molecule of oxygen 16. So water that contains oxygen 16 will evaporate far more readily than water molecules that contain oxygen 18. Okay, so that means when you start evaporating water, you're going to get lots and lots of water molecules containing oxygen 16 going into the atmosphere, and far fewer water molecules containing oxygen 18. So the other thing that happens is when you begin to make your water condense to form things like water droplets, so i.e. rain, well, oxygen 18, because it's denser, will naturally condense more efficiently than oxygen 16. So we have a situation. Number one, there is less oxygen 18 going into the water that's evaporating from the oceans to begin with, and then as soon as that water in the atmosphere begins to cool down a little bit and it begins to coalesce to form droplets of condensation in the atmosphere, and those drops of condensation get large enough to form rain, well, that rain is going to be very, very rich in oxygen 18. So that means relatively little oxygen 18 evaporates in the first place, and a lot of the oxygen 18 that's in the water in the atmosphere will be lost very, very quickly the first time the water begins to turn into rain droplets. And so this means that water vapor will be enriched in oxygen 16 versus oxygen 18. It means that any precipitation that forms from that water vapor will be enriched in oxygen 18 versus oxygen 16. So how does this help us exactly? So what we notice is during glacial periods, we obviously have evaporation of water, especially in the equatorial regions. That water goes into the atmosphere, and that water vapor will be very, very rich in oxygen 16 and comparatively less rich in oxygen 18. Now, obviously, as that water begins to move from the equatorial regions towards the poles, temperatures are going to drop. That water is going to start to condense to form droplets of condensation, and that condensation is going to fall out of the sky in the form of rain, and that rain is going to take large quantities of oxygen 18 with it, leaving behind lots of oxygen 16 rich water vapor. Now, that water vapor will continue to move to higher and higher latitudes towards the poles, and so eventually when that water vapor cools down enough, it will form snow. That snow will fall in these high latitude areas, and eventually once you build up enough snow, that snow gets compressed, and that will form glacial ice. And glacial ice locks up that water. That water will take a very, very long time to be released again. It's locked in the form of ice. It's going to take, thousands of years for that piece of ice to make it to the point where it's going to melt again and release that water back into the oceans. So once this oxygen-16 water vapor is locked into the glacial ice, it's stuck there for very, very long periods of time. And obviously the more glacial ice you have, the more oxygen-16 gets locked in it. And so during these periods of very, very large glaciations, we see the amount of oxygen-16 in the oceans decrease relative to oxygen-18 because lots of it is getting locked in the ice and it's being held there. It can't escape. So this just pretty much covers what I've said there. So what we can do then is, as shelly organisms take one oxygen atom from water to make carbonate, obviously the oxygen-18 oxygen-16 ratio of the water will be reflected within the calcium carbonate that's used to make the shell. And so when we measure that calcium carbonate, we can look at the ratio of oxygen-18 to oxygen-16. So by finding shells with high oxygen-18 oxygen-16 ratios, we can see, I do apologize what's happened here. Well, that was very strange. I don't know what happened there, everyone. Let's continue. So by finding shells that have a high oxygen-18 to oxygen-16 ratio, we can see where large-scale glaciations occurred. So we see the amount of oxygen-16 dropping, and comparatively the amount of oxygen-18 goes up. Now, when we have periods of glacial retreat, so the interglacials where things get warmer, we see the amount of oxygen-16 in the oceans increasing, and so we see the oxygen-18 to oxygen-16 ratio getting lower. So the most important thing to remember is that in each of these three pieces of evidence, the type of foraminifera, the coil direction, and the oxygen isotope values, we only get very coarse data. We can say the surface water was cold or the surface water was warm. We don't actually have a number. We can't definitively say, yes, the surface water temperature during this period was exactly 7.58 Celsius. We can't do that. This data just isn't that refined. So another interesting situation we have is that we cannot correlate the cooling and warming events we see in the oceans with the terrestrial sediments because there's a lag between the two. So on land, we can see the glaciers begin to expand, and we can see that in the glacial sediments. Well, obviously, it takes a little while for that expansion to be seen in the seawater, and therefore in the calcium carbonate that's used to make the shells of the animals. And so, as soon as the glacial ice begins to extend itself on land, we don't see an instant decrease in the amount of oxygen-16 in the oceans. The decrease actually takes a little while to occur, so there's a very poor correlation between glacial events on land and the signals that we see due to those glacial events in deep marine sediments. Okay, so let's pause here. So pause meditation, get up, get a glass of water, have a walk around, and come back in a few minutes, please. Okay, so let's look at the onset of the last ice age. So the onset of the last ice age actually has a very long build-up. It takes a very long time to get there. So around 40 million years ago, that's during the Eocene, we begin to notice a sudden decrease in the ocean surface temperature at high southern latitudes. That's towards the South Pole, while deep ocean temperatures decreased globally. So during this period, we see the deep water across the entire globe gets colder, and we see, especially in the southern hemisphere towards the South Pole, we see the surface water temperatures also begin to decrease. So if we remember, during this period, we obviously towards the end of the Cretaceous, we had the complete breakup of Pangaea, and this obviously had very significant effects for water circulation in the oceans. So we also need to remember that we had a body of water which was referred to as the Tethys Ocean that sat approximately where the modern-day Indian Ocean was, or is, should I say, and the Tethys Ocean helped to give warm water to the surrounding oceans. So what happens is by the Oligocene, that's the late Paleogene, about 28 million years ago, we see this flow was constricted, and by the Miocene, 14 million years ago, it stopped altogether. So what's actually happening? So this diagram is going to kind of demonstrate what's happening. So here's the situation around 40 million years ago. Obviously North America, South America, Africa, Europe, Asia, Australia, and Antarctica. Now, the first thing you notice around this point here is we begin to get essentially a circulation of water around Antarctica. And so this is why we see this sudden decrease in ocean temperatures at high southern latitudes around this time. Now, in terms of what's happening during this period, we see the global deep water temperatures begin to drop. But in terms of the surface water temperatures around 40 million years ago, we see they're actually quite warm. And that's because we have warm water coming from this Tethys Ocean / Indian Ocean region, and it's moving up here between Africa and Europe, going into the North Atlantic. It's coming around the southern portion of Africa into the South Atlantic. And obviously as it exits here, it comes through this gap here, then it comes into the Caribbean, and it can pass between essentially North America and South America and enter the Pacific. And so this circulation of warm water, which is going on around during the Eocene, helps to keep these ocean temperatures, these surface water temperatures, higher around this time period. Now, 14 million years ago, things have changed significantly. Africa's made contact with Europe, and so it means the water can no longer squeeze, this warm water from the Indian Ocean can no longer squeeze between Africa and Europe, so it can't go that way anymore. And some of it can still go around the southern horn of Africa, but once again, not as much. And so by this point as well, we also have South America and North America beginning to interact and form one solid landmass as the two continents begin to join together via Central America. And so once again, so what this means is we now have isolated bodies of water. So we have the Indian Ocean, that's got obviously Asia to the north, Africa to the west, and Australia to the east, and it's cut off by the Antarctica to the south, so that's one body of water. We have the South Atlantic, that's cut off by essentially Africa to the north and to the east, South America to the west, and Antarctica to the south. And then we have the North Atlantic. Obviously, we've got Europe and Africa to the east. Essentially, we've got North America to the west. We have essentially the constricted portion of the Atlantic here to the south, and we have essentially Greenland and northwestern Europe to the north. And so we end up with these restricted bodies of water. We obviously have the North Pacific and the South Pacific as well, and we can see that in this diagram here. This shows you the circulation patterns of these bodies of water. And so what we now have is we now have these isolated bodies. So we see around 40 million years ago, because the warm water is no longer exiting this Indian Ocean / Tethys Ocean area and entering the North Atlantic, the South Atlantic, and the Pacific, we see global temperatures begin to drop, and that's going to cause global climatic temperatures to also decrease. So as I said, this caused ocean temperatures to begin to drop, especially in the North Atlantic. And also, as I said, at the same stage, we see the appearance of the Antarctic circumpolar current. And what this does is it completely separates Antarctica from the rest of the environment. So the circumpolar current operates here, and essentially it acts as a barrier. It stops warm water from the Indian Ocean, making it south towards Antarctica, and it stops warm water from the South Atlantic, also making it south, and also from the South Pacific, also making it south. And so it separates Antarctica from this warm water, and it means Antarctica is surrounded by a band of very cold water, and that helps to keep Antarctica colder than it probably should be. And so this is quite interesting. That helps to encourage the formation of large quantities of ice on Antarctica. And that's obviously going to have a significant glacial effect because ice reflects solar radiation. That's going to also help to drive down global temperature. So by the middle Miocene, around 40 million years ago, the Antarctic circumpolar current is established, and we have this decreasing global temperature due to essentially the constriction of warm water moving from the Indian Ocean into the Atlantic and the Pacific. And that's going to help to further accelerate global cooling. So we see a brief warming trend during the Pliocene, we see a brief warming trend, and then during the Pliocene, we see glaciers begin forming in the northern hemisphere around 2.6 million years ago. So what's happening is, from about 14 million years ago to around 2.6 million years ago, we have a general downward trend in terms of global temperature. Things are steadily getting cooler and cooler and cooler, and then all of a sudden, around 2.6 million years ago, we see the first hints of large-scale glaciation beginning to start in the northern hemisphere. So okay, so here we go. So this kind of shows you the climatic trend during the last, during the Cenozoic, so down to about 66 million years here, and the present day here. So what you'll notice is, if you look at the trend of this graph, you will see that on the whole, it's on a downward slope. So yes, there is some significant change during this period, but on the whole, if you add it all together, what we have is a steady decrease in global temperatures throughout the Cenozoic. And obviously, as global temperatures decrease, the amount of ice is going to increase. So the decrease in global climate that led to the Ice Age was not rapid. It's been occurring over the last 66 million years. It's part of a consistent global trend. So we have the oxygen isotope data from deep sea cores, and that indicates that during the last 2 million years, Earth has had at least 20 warm-cold cycles, as we touched on earlier. And these warm-cold cycles would have had a temperature fluctuation of anywhere up to about 10 Celsius. That's a pretty significant change. So areas proximal to continental glaciers and ice caps experience short, cold summers and long, wet, cold winters. That's to be expected. If you're right next to an ice cap, conditions are obviously going to get rather chilly. Your summers are going to be relatively cold and relatively short. Your winters are going to be relatively long and relatively wet. So as the ocean temperatures were lower during the Ice Age, and the air temperatures were also lower, the amount of evaporation from the oceans will have decreased. And this caused much of the world to become drier than at present. However, there were exceptions. So we've already touched on the fact that as the ice sheets moved southwards, it began to push the temperate band more towards the equator. And so this means that the temperate band that now covers most of the United States and Europe got pushed towards areas like the Sahara and the southern states of the US. That led to the growth of very, very large forests. In the case of North America, we have an interesting situation where we have a constant region of high pressure, which is sitting over the ice sheet that's covering North America. So if we go back to this diagram here, this ice sheet here has a huge area of high pressure sitting right there. And so that means any humid air that's trying to come northwards hits this high pressure region and it just bounces straight off. And so that means it forces all this warm air to come this way, bounces off, and so all the rain is falling here across the southern United States and Mexico. So this caused the southwestern United States and Texas to be considerably wetter than they are now. So another tool that's proven useful in the study of climate during the Pleistocene and Holocene, especially the Holocene, is pollen analysis. So we can look at the pollen grains left by plants, and we can use them to infer temperature. So the technique looks at pollen grains. So if you remember that pollen is the male reproductive cell released by angiosperms. And we can actually collect those pollen grains from the sediments and we can analyze them. Remember, the pollen is covered in a thick waxy coating that means it can be protected for relatively long periods of time. So the pollen grains can exist for extended periods within sediments. So pollen grains are carried by the wind, and they will collect in areas like streams, so rivers, lakes, swamps, bogs, and near-shore marine environments. So as geologists, all we have to do is come along later, take the sediments, sieve them to get the pollen grains out, and we can look at what pollen was around at the time, and therefore we can infer the types of plants that were around at that time. And obviously the plants will be a direct reflection of the climate. So let's have a look at this example here. This is from the Chatsworth Bog in Illinois. And so what we're going to look at is we'll start with, you can see over time, so time 14,000 years ago here, 1,000 years ago here, you can see that over time there's been a significant change in the amount of different change in the amount and types of plants that are present in that area. So around 14,000, 13,000 years ago, we have lots and lots of spruce. So spruce is, of course, a tree. It's a conifer. And so spruce is commonly associated with what's referred to as the boreal forests. That's the kind of forest that covers most of Canada and most of northern Russia. Those are cold weather forests. And so that would suggest that around 14,000 years ago, the Chatsworth Bog area of Illinois was quite cold. And, that would be consistent with the fact that the area was relatively close to the edge of a huge ice sheet. That makes perfect sense. Now, what we begin to see around 12,000 years ago, this approximately is the boundary of the Holocene, the Pliocene-Holocene boundary, we begin to see the appearance of ash, followed by elm and oak. Now, these are deciduous temperate trees. So these trees do not like extremely cold weather conditions, and so the appearance of these trees tells us that the temperature in this area is slowly dropping off. Slowly getting warmer. So typically when deciduous trees move into an area, often the first deciduous tree to grow is ash, followed by eventually elm, and then oak establishes itself. Now what happens is the oak will typically begin to outcompete the ash and the elm. And so what we see happening is initially, as the temperature begins to rise, the ash population begins to increase. Same with the elm population. But then eventually they begin to be outcompeted by the oak, and we see that the amount of ash and elm decrease. So from about 12,000 years ago, we see a significant increase in the abundance of oak in the Chatsworth Bog region. So as we're moving up along, we then see the appearance of grasses. Ragweed begin to make its appearance as well. And so what's happening here is it's telling us we're moving from a period where we have lots and lots of tree cover to a period where we have oak trees which are separated by areas of grassland. Okay, so as the oak has begun to outcompete the ash and the elm, if you've ever been to an area where lots of oak trees, what you'll notice is oak trees like to grow relatively spread out, and so that means there's space in between them for grasses to begin to grow. And so that's what's happening there. We see this shift from very heavily forested land here to a mixture of oaks and grasses here. And then steadily over time, we also then begin to see the appearance of goosefoot. That's telling us that conditions are getting even warmer. In fact, they're actually getting a little bit drier. That's why the goosefoot is making its appearance here. We're actually seeing the conditions going from relatively, well, comparatively speaking, more wet here, and right towards the end, around 1,000, 2,000 years ago, conditions begin to get noticeably drier. And so just by looking at these pollen grains, we can actually work out the history of the plant life in an area, and as mentioned, that's a direct reflection of the climate. So by looking at the oxygen isotope data and by looking at the pollen analysis, we can get a good idea about what's happening from a climate point of view on land and in the oceans. So what we can also do is, in some areas, if we're lucky, we may have trees that go back, hundreds, maybe even thousands of years. We can also have, of course, trees that have been fossilized. And so we can also look at the tree rings for those trees. And so that allows us to look at the growing seasons for these trees. So remember, a tree ring essentially represents 1 year's growth for a tree. The big thick tree rings are good years, so that's typically warm years, and the thin tree rings are typically poor years, that's relatively cold years. And so by looking at the tree ring, so we can see, this year was good, this year was bad, or this decade was good, this decade was bad, or this 100 years was good, this 100 years was bad, we can combine that data with the pollen analysis and the oxygen isotope analysis, and obviously the data from the foraminifera as well, and we can begin to get an idea of exactly what's happening with the global climate during the last 2.6 million years. So the episodes of glaciation occurred during these periods of... Oh, I do apologize, I've skipped a slide there. No, I didn't. I skipped a paragraph. So, okay. So we have all this information that we can gather together that gives us an idea of whether conditions were warm or whether conditions were cold. Once again, remember, none of this analysis gives us a solid number. Okay, we can't say, on Tuesday, the 15th of December in New York, the temperature was this. We can't do that. All we can say is, right, during this period of time in the area around New York, conditions would have been either warm or cold. So obviously we then combine, we have the tree ring analysis, and what we see is the data indicates a continuous warming pattern until around 6,000 years ago. And at this point, the climate in the northern hemisphere becomes cooler and more humid, which favours the growth of valley glaciers. So if we just go back up, here we go. So around 6,000 years ago, we're going to be somewhere around here. Okay, all of a sudden, bang, temperature begins to drop off a lot faster. So this is called the warm climate of the Pliocene. So we see the temperature go up, and then it just nosedives. So, as I said, at this point, the climate in the northern hemisphere becomes cooler and more humid, which favours the growth of valley glaciers. And this episode of glaciation occurred during this neoglaciation. It's called a new glaciation. So the most recent glacial episode was something which is referred to as the Little Ice Age, and that actually occurred around 1500 to 1800. So essentially, during that time period, we have the period where we've got King Henry VIII in England, going all the way through to let's face it, the War of 1812, where the British and the Americans had a slight falling out, shall we say. So, that's a pretty significant period of time there. So this Little Ice Age essentially is marked by periods of relatively cool, damp summers and relatively cold winters. So if you've ever wondered, why, certain authors, will typically, when they're discussing things like Christmas, will always be, describing how Christmas is always, white and there was snow all over the place. And that's very often because these authors were writing during this Little Ice Age. And for them, winters always were snowy. That's just the way it was, because we're in this Little Ice period, Little Ice House period. However, around 1800, from around 1800 onwards, things steadily warmed up. So that was a relatively small ice age that occurred during the Holocene, but that was relatively minor. Most of the glacial events that occurred during the Pleistocene, and most of it really kicked off around 6,000 years ago, when we see this sudden drop in the global temperature. So so we can see things really begin to drop off around 6,000 years. Sorry, I'm going to go back for 1 second. Do you know what? I've just suddenly realised I got my numbers completely wrong there. Do you know what? I am just going to scrap this slide altogether, and I am going to go back to the start because I made a mistake there. So please forgive my huge mistake here. Let's try this one again. Okay, so the polar analysis, that was fine. The polar analysis data is all good. So we can combine that with tree ring analysis, and that obviously gives us an idea of the temperature, not only globally, but also in certain regions. So this data indicates that since the Holocene started around 12,000 years ago, we've had a continuous upward trajectory in terms of global temperature. Things have been getting warmer. Okay, now that was until around 6,000 years ago. That was essentially where we had this peak of temperature during the Holocene, and then we begin to see a little bit of a drop down. Okay, so around 6,000 years ago, we begin to see northern hemisphere climates especially become a little bit cooler and a little bit more humid. So this is referred to as a neoglaciation. It's a small glacial event within essentially a period of relatively little global glaciation going on. And also during the Holocene, we have this Little Ice Age that runs from 1500 to 1800. And, obviously that's reflected in things like literature, and the fact that we always, during this time period, people that are writing, especially, books that are centered around Christmas, will typically discuss how Christmas is always, really white and, everything is covered in snow. So that makes more sense. I do apologize. I completely misread what I was saying there and got myself terribly confused. Anyway, so on to the final point here. So the cold temperatures had a serious effect on crop yields during this time period. So 1500 to 1800 was a period of relatively poor crop yields. So especially in countries that had a subsistence agriculture based economy. well, they suffered rather badly. And so what we see during this time period is we see lots and lots of small kingdoms, especially in Europe, beginning to join together to form larger kingdoms in order to pool their resources more effectively. Okay, so now, do you know what? Let's take a quick break now, and then we'll move on to the formation of glaciers next. So pause the presentation, get up, have a walk around, and come back in a few minutes, please. So before we start with the formation of glaciers, let's just take a second to do the code word for this presentation. The code word is going to be Greenland. I repeat, Greenland. So make a note of that, please. Okay, so the formation of glaciers. So during the Pleistocene, we had all types of glaciers, and that's valley glaciers, ice caps, and continental glaciers, becoming far more widespread and far more extensive. So at present, there are only two continental glaciers, as we've discussed. We have Antarctica and Greenland. But during the Pleistocene, ice covered approximately 30% of the Earth's land surface. At present values, it's around 10%. And most of this coverage occurred in the northern hemisphere. So the glaciers that formed during this time period, obviously, as we've also touched on, advanced and retreated, and we know that this occurred 20 times. And this advance and retreat will produce, essentially large quantities of topography in these glacially affected areas. So essentially the action of the glaciers and their growth outwards during this time period is going to have a very serious effect on the topography we see in the areas that the glaciers covered. We also know that during this period, in the more mountainous terrain, because global temperatures were lower, that also encouraged the formation of large valley glaciers. So glacier formation is actually a super simple process. So if an area receives more snow in cooler periods than melts in warmer periods, then you're going to have a net accumulation of snow over time. So once the snow accumulation occurs, the snow at the bottom will be compressed by the weight of the snow above. And this compressed snow will turn into what's referred to as glacial ice. So this ice will then begin to flow in response to the pressure of the snow on top of it. So essentially, if you have a column of ice 40 meters high, the weight of that 40 meters of ice will cause the ice at the bottom of the column to begin to flow like a liquid, just due to the weight of the ice pushing down on it from above. Now, this plastic flow, this deformation, occurs after you have this magic 40 meters of ice built up. So what happens then is the ice will then naturally flow downhill under gravity, and it will flow from what's referred to as the zone of accumulation, and that's where the addition of snow exceeds the losses, to a region which is referred to as the zone of wastage, and that's where the losses of snow and ice exceed the amount added. So as long as a glacier has a balanced budget, so losses don't exceed addition or vice versa, the glacier will not change. It will stay exactly the same length. However, if the budget is positive, so you have more ice forming, then the glacier will advance. If the budget is negative, so you have more melting of ice than you have new ice being made, then the glaciers will retreat. At the moment, most glaciers globally are in a period of retreat. So essentially we have global temperatures going up. That's causing more ice in the glaciers to melt. And so obviously that means we have a retreat of the glaciers. So this diagram is taken from the textbook. It kind of summarizes what's going on. So up here we have the zone of accumulation, where the amount of snow and ice being formed exceeds the amount being lost due to melting. And this snow and ice will move typically in one of two ways. Obviously, we discussed it will move both under gravity, and it will also move due to plastic deformation. So the weight of all the snow and ice here will push the ice down at the bottom, squishing it, causing it to deform and making it flow away from the high pressure area. Obviously, you have lots of snow and ice down here pushing on the ice. That means lots of weight, so the ice will naturally flow into an area that has lower pressure. Eventually that ice will flow into a region where we have essentially a net loss. So we will have more ice melting than is being added in that region. And so this means essentially the ice will begin to melt, and eventually the glacier will obviously stop because all the ice will melt away. And this is an area that's often referred to as the glacier's nose or the glacier's head. So obviously glaciers are going to have a very significant effect on the environment. They're very big, powerful things. Glaciers are essentially massive bulldozers. So very large glaciers moving over the Earth's surface have the capacity to reshape the Earth's surface significantly. They can affect things like topography, and they will produce very distinctive glacial landforms. So a glacier, in theory, has the capacity to destroy hills. It can just plow through them. So, that's obviously, this power that the glacier has will produce very, very distinctive landforms, very, very distinct morphology to the land that essentially has been affected by glacial processes. So it should be remembered that the effects of the Ice Age were not limited just to glaciers. So the expansion and retreat of the ice sheets produced marine regressions and transgressions. Obviously, when you have a very, very large glacial event, you have more ice forming, that's locking up seawater, and that's obviously going to lead to a marine regression. When that glacial ice melts, it's going to put water back into the oceans, and that's going to lead to a marine transgression. So that's obviously going to affect coastal regions. So even areas that are a long, long way from the glaciers will experience changes in their climates due to these marine transgressions and regressions. Of course, as we've already touched on, mass glaciation will also affect global climate. The more ice you have, the more solar radiation gets reflected back into space, and that's obviously going to, change global climates. And we also have the situation where areas that were once covered by very, very thick glaciers are currently undergoing the process of isostatic rebound. So isostatic rebound is essentially the result of the weight of the ice. So if you had an area of the Earth's crust, so let's say Ontario in Canada, that area would have been covered by a sheet of ice on average about 3 kilometers thick. So quite a substantial sheet of ice. And that sheet of ice obviously has it weighs a lot. And so it's actually going to push down the Earth's crust. The weight of the ice is so great that it pushes down the Earth's crust. And so what happens is obviously when the ice melts, well, the Earth's crust is going to bounce back up. So that's isostatic rebound. So the weight of the ice pushes the Earth's crust down. As soon as the ice is gone, the crust bounces back up. Now, this isn't a fast process. It takes place over thousands of years. So at the moment, there are, large areas of Canada are still rising. So they're still going up after, 12,000 years after the last ice age finished. So, that's another effect that we're seeing due to glaciation. Okay, so now we're going to look at some of the landforms that are produced by glaciations. So continental glaciers, the very, very big glaciers, will produce things which are referred to as ice-scoured plains. So these areas have little to no soil because the glaciers ploughed it off. They have a very subdued topography, so the areas are very, very flat. Once again, that's because the glacier has either planed off areas of topography, so hills have been leveled out by the force of the glacier, they've been eroded away, or topographic lows in the region have been filled with glacial sediments. And so that means the topography in the area will become very, very flat. So highs get eroded away and lows get filled in with sediment. These areas also have polished and striated bedrock due to the movement of the glacier over the bedrock. And the area has poor surface drainage because the area has very, very subdued topography. If there's no gradient, the water can't flow anywhere. So that means these ice-scoured plains typically have lots and lots of lakes on them. So if we just look at this diagram here, these are two areas of ice-scoured plains. This is one from Canada, and this is one from Wisconsin. So you can see both these areas are very, very flat. They've been planed level by the force of these continental glaciers moving over them during the last ice age. You can also see there's no soil, you're straight on the rock. You can see that the area has very, very poor drainage. Okay, the water's not going anywhere, so it forms lots and lots of lakes. So that's it. Both of these are classic ice-scoured plains. So this is the situation, of course, as the glacier moves over, obviously it's eroding all this material beneath it. It's essentially bulldozing all of the material out of the way, leveling, polishing the surface underneath it. And of course, once the glacier retreats, it leaves behind the ice-scoured plains. So for valley glaciers can form two distinct types of glacial landforms. So remember, these ice-scoured plains are for continental glaciers, very, very big glaciers. Valley glaciers will produce features which refer to as cirques and U-shaped glacial troughs or U-shaped valleys. So this is an example of a cirque here. So cirques will typically form on the edges or on the sides of mountains. And so a cirque essentially is a very small glacier. So it doesn't have, it doesn't flow for miles and miles and miles. It'll, this distance here maybe will be a few kilometers. And so what you have is you have a little depression on the side of your mountain. That depression begins to fill with snow. Obviously that snow gets compacted to form glacial ice. And obviously over time, the weight of that glacial ice will cause the ice to be pushed downhill under gravity out of the cirque. And it will produce these very small bowl-shaped depressions on the sides of mountains and on the sides of ridges. And so cirques are very, very common in mountainous terrain. On the other hand, when you have a river of ice that's moving through mountainous terrain like a river, it's going to move down a valley. So if you remember, valley glaciers have topography on one side and topography on the other side, and so the ice is trapped in the valley in between these two areas of high ground. Now, as the ice moves along, obviously it will polish the rocks, so you'll have very, very smooth rock here. It will produce a very, very flat bottom to the valley. But you can see quite clearly the valley will have a very, very distinct U-shape to it. And so this is a very, very common feature that we find with valley glaciers. They will very often form these very, very distinct U-shaped valleys. So another thing that we see is both continental and valley glaciers will deposit a chaotic mixture of poorly sorted sediment at the glacier's margin. Of course, we know this is called glacial till. And this glacial till will build up to form things which we refer to as moraines. So here's our glacier again. And at the edge of our glacier where it's melting, all the sediment that's contained within the ice is going to be deposited. It just piles up along the edge of the glacier here. And over time, it builds up a pile of glacial till, which we refer to as a moraine. And so as a geologist, we can come along and we can look for these moraines, and these moraines are quite helpful to us. So, as I said, the melting glacier produces substantial quantities of water, and that water will then erode the moraine, if I go back to this diagram here, and it will wash away the glacial sediments, the glacial till, and that produces what's referred to as the outwash plain. So we have the glacier, we have the moraine, and in front of the glacier we have the outwash plain, which is where the water from the melting ice transports the sediment from the moraine and takes it away from the glacier downhill in a river. So these are some of the features that we see. So moraines are arguably very important when it comes to discussing glaciers. So moraines are deposited at the glacier's termination, its terminus. And these are often referred to as terminal moraines. So the moraine that forms at the maximum extent of a glacier is the terminal moraine. That's the moraine that forms furthest out. So up here, we actually have a picture of the sediments deposited in the Great Lakes region during the last ice age. So here in yellow and peach, we have the outwash plain. So that's where sediment's being taken from the moraines and redistributed by very, very large rivers. So that's definitely not actually, the glacier edge. Now, what we have here in green is we have these end moraines, they're called. So if we follow a line across here, So if we come around here, we follow the very, very edge of this green line. This marks the maximum extent of the ice during the last ice age in the Great Lakes region. So that's what we can do. So this moraine that's furthest out is referred to as the terminal moraine. And here we can see, here we have a terminal moraine for the Werde Glacier in Greenland. You can actually see it here. It's this dark line here. This is just essentially where sediment is piled up when the glacier melted. So this is the outwash plain here. And as you can see, the glacier is now retreating, leaving behind this the terminal moraine here, and behind it we have what's referred to as a ground moraine, which we'll come on to in a second. Now, as a glacier retreats, once again, it's not a smooth process. It doesn't just start retreating and just keep retreating. What's going to happen is your glacier is going to retreat for a few years, and then it's going to stop for a bit. And when it stops for a bit, it's going to form a new moraine. And then the glacier is going to start retreating again. And so as your glacier retreats, it's going to retreat, stop, form a new moraine, retreat, stop, form a new moraine, retreat, stop, form a new moraine. So there are, as you can see, behind the terminal moraine here, there is moraine after moraine after moraine. Now these are referred to as recessional moraines, and they're showing us the retreat of the glacier. So these recessional moraines are just formed by a temporary pause in the rate of the retreat of the glacier. So the final type of moraine is a ground moraine. So the ground moraine is formed as the glacier retreats. Okay, so both the terminal moraine and a recessional moraine requires the glacier to stay still for a period of time, so sediment can build up and form the moraine. A ground moraine, on the other hand, is formed as the glacier is retreating. So as the glacier retreats, it just simply drops sediment as it goes. And this layer of sediment that drops as it goes is referred to as the ground moraine. So here we have a picture. So this is our glacier here. As you can see, it's a valley glacier, so it's retreating uphill there. So the glacier itself has actually paused for a bit. You can see you actually have a buildup of material here. That's your moraine. And in front of it here, you have this plain. And this is the ground moraine. So this is just a sheet of material that's been dropped as the glacier has been melting and retreating. So a ground moraine doesn't build up, doesn't actually form any topography. It's just a layer of material being deposited as the glacier retreats. So a glacier will form essentially three types of moraine. There's the terminal moraine that marks the maximum extent of a glacier when it's at its absolute biggest. There are the recessional moraines. They form as the glacier retreats. So every time the glacier stalls as it's retreating, it will form a recessional moraine, and then it will start retreating again. And then there are ground moraines, and ground moraines are formed as the glacier is moving, so that means it's dropping a layer of sediment as it retreats. Okay, so those are some of the things we look for when we are thinking about glaciers. Those are some of the features that we try and hunt for when looking at glacial sediments. So now let's have a quick think about sea level changes due to these glaciers. Now, we've already touched on the fact that as glacial ice expands, it's locking up water from the oceans, so global sea levels will drop. So at present, glaciers contain around 28 to 35 million cubic kilometers of water. And obviously all that water came from the oceans. So during the Pleistocene maximum, that's where we had the maximum amount of glaciation. That number was around 70 million cubic kilometers. And that would have been enough to lower global sea levels by around 120 to 130 meters, around 20,000 years ago. So, and you can actually see it here, there it is, there. So these low sea levels would have meant that large portions of the modern continental shelf, which are currently underwater, would actually have been above sea level because global sea level was very, very low. And so this means that the Bering Straits would have been essentially a body of land. You could have walked straight from Alaska to Russia and you wouldn't have gotten your feet wet. The United Kingdom would have been joined to France as well. Sri Lanka would have been joined to India. Australia would have been joined to Papua New Guinea, for instance. So just to give you some idea of what would happen if we melted all the water that's held in the glaciers now, it would cause global sea levels to increase by somewhere in the region of about 70 meters. So if that happens, if we were to melt all the water in the ice caps that we have now, a lot of the major coastal cities, so New York, Houston, London, any city on the river, Paris, cities like Rome, would be in a lot of trouble, because obviously those cities would be inundated, very, very quickly. So we've already touched on isostasy. So isostasy is due to the weight of the ice. So as we mentioned, during the last ice age, you would have had an ice sheet that would have been about 3 kilometers thick on average. So the weight of the ice sheet will have pushed down on the continental crust, and so it pushed the continental crust down into the mantle. Now, once the ice sheet began to melt, and once it's gone now completely, obviously that means that the weight is gone, and so the continental crust will naturally bounce back up. And as we've already discussed, this is called isostatic rebound. So the weight of the glacier pushed some areas 300 meters below their pre-glaciation levels, and they're still rebounding now. And this diagram here kind of shows you the amount of isostatic rebound being felt by areas in Canada. So these areas are in meters, and so these areas have experienced a rebound of 100 meters. These areas slightly less, so 20, 30, 40. So you can see there was clearly large quantities of ice located here and here. That's where the maximum amount of ice would have been. And obviously the amount of ice was getting lower as we moved in this direction here. So the ice sheet was getting thinner as we moved this way. And so obviously because there was more ice here, the ground got pushed down further. And so once that ice was gone, it's obviously experienced a much higher rate of rebound. So the effects of isostatic rebound can actually be seen quite easily on the landscape, and you can actually see it affecting human structures. So if you go to places like Scotland, and if you go to areas like Canada, you'll be walking along near the coast, and you'll see there are areas where you have docks, and these docks are several hundred meters inland from the modern coast. It doesn't make any sense. The thing is, a few hundred years ago, those docks would have been on the coast. But obviously, since the dock was built and the present day, that area of land has been rising, and now the dock is several tens of meters, hundreds of meters inland from the modern day coastline. So when we look at things like isostatic rebound, we can see things like this. So this is Nunavut in Canada, and you can actually see the effects of isostatic rebound on the beach here. So you can see the beach has all of these lines on it, and these lines essentially represent the high tide marks, over tens of years, decades. And so you can see over decades, this area of land has been slowly rising. So the coastline would have been here, and over time it's been dropping to the present point here. So this map here actually shows you the rates of global isostatic rebound. So you can see, obviously, the more orange or blue the area is, the more isostatic rebound it's experiencing. So you can see areas like Canada, northern Greenland, Scandinavia, and very northern Asia, so essentially the islands north of Asia, are all experiencing quite high rates of isostatic rebound caused by the melting of the ice from the last ice age. You can actually see down here, we actually have the effects of the end of the last ice age and more modern melting taking place down here in Antarctica, causing the ice sheets here to thin out, and we're actually seeing these areas of Antarctica are beginning to bounce up as the ice sheets get thinner in this region over here. Now, if we look at the United Kingdom, this diagram here shows you the areas of the United Kingdom that would have been under ice during the last ice age. And we can actually see, if we look at the United Kingdom now, the areas that are undergoing isostatic rebound, or so they're rising, are marked in green, and the areas that are sinking are marked in red. And so what's happened is in the United Kingdom is actually acting like a giant seesaw. So the weight of the ice in Scotland pushed down Scotland, northern England, and essentially northern Wales and a bit of Ireland, and that caused the southern portions of the United Kingdom and Ireland to rise up. And obviously, once that ice has disappeared, these areas here have started going up, and so that's meant these southern coastal regions have been dropping down, which I think is quite an interesting little, side note. So, obviously, the melting of glaciers is going to produce very, very large quantities of water. And this water is going to move, obviously, via rivers, and it's going to gather in areas where we have topographic lows. And so it's going to form lakes, large quantities of lakes. So during the Wisconsin, that's 85,000 to around 11,000 years ago, many now arid parts of the United States, especially in the southwestern states, had very, very large lakes. Now, we've already discussed that these areas down here would have experienced a lot more rainfall on average because the temperate zone, which normally sits up here, had been pushed south by the expansion of the ice sheet. And we also had the high pressure region sitting over these ice-covered areas that meant that all the humid air that was coming off the Pacific would be moving north. It would hit the high pressure region and it would bounce back south again. So it would dump all the rain in this region as well. So these areas were very, very wet anyway. And then on top of that, you had all the melting from the ice up here, also dumping water into this area via very, very large rivers. And so what would have happened is you would have formed lakes next to the glacier and you would have formed lakes a long way from the glacier. So the lakes that formed a long way from the glacier or distal to the glacier are referred to as pluvial lakes. And their existence is a reflection of the cooler temperatures and the movement of the temperate zone south and the resulting cool, wet summers, as we've already discussed. So the existence of these pluvial lakes is denoted by the fact that in these areas, which are now very, very dry, we can see things like wave-cut cliffs. So we can see that there have been areas of cliff faces that have clearly been eroded by the action of waves. Now, clearly, if you are in, areas like, Arizona, Nevada, those areas do not have large bodies of water, and so that obviously implies if we have these wave-cut cliffs, well, clearly there has to have been a large body of water there in the past. We can also find beach deposits associated with the margins of these lakes. We can see deltas produced by rivers entering these large lakes. We can see the lacustrine or lake sediments associated with the lakes, and we can see freshwater fossils. So, for instance, this area here, marked out as Lake Manly, this is Death Valley. And if you look in the sediments from the last ice age deposited in that area, you'll actually find freshwater fish fossils. If you've ever been to Death Valley, you will know with 100% certainty there are not any freshwater fish alive in Death Valley now. So that would imply that at some point in the past, very recent past, Death Valley was actually under a large body of water. So, as I said, the classic example of a pluvial lake is Lake Manly, and that's located in the area that is now modern-day Death Valley. So Lake Manly was quite big. It was 145 kilometers long and 180 meters deep, and it was sat in the modern Death Valley Valley. So this is a false color image of Death Valley. So Death Valley has high ground over here to the west, and it has high ground over here to the east. And so this area here, the valley itself, would have been filled with a very substantial lake. And obviously what happened is as the ice sheets began to retreat, the area that is now the modern day Death Valley began to become drier, and so obviously the lake began to evaporate away, and that left very, very large quantities of evaporite minerals behind. And in fact, a great example of that is over here. So this is Lake Bonneville, arguably the largest of the pluvial lakes produced during the last ice age. And as Lake Bonneville evaporated away, it left behind the Great Salt Lake, which is located next to Salt Lake City. So that's where That's where essentially the Great Salt Lake came from. The evaporation of all this water associated with Lake Bonneville, and that body of water was obviously formed during the last ice age. Now, you're obviously going to have lakes next to the glacier as well. These are referred to as proglacial lakes. So they'll form proximal or next to the glacier, and they're formed in areas where meltwater accumulates along the glacier's margin. So a good example of that is a lake called Agassiz, and it formed in this manner. So it covered an area of approximately 250,000 square kilometers, and it included areas of North Dakota, Manitoba, Saskatchewan, and Ontario. So here we go. So here's Lake Agassiz. You can see it's a very substantial body of water. Obviously, we have the Great Lakes over here as well, and we have several smaller lakes associated up here, like Lake McConnell. So obviously, these lakes are formed in topographic lows next to the glacier, or they can form in areas where a moraine has formed, and that acts as a barrier, and the water gets trapped behind that moraine that can't escape. So as the ice sheet melted, so as this ice sheet here melted and it moved northwards, obviously it allowed these lakes to drain in a northerly direction into Hudson Bay, which is located here. So sediments deposited in the proglacial lakes range from muds to gravels. Now remember, because these lakes are located right next to the glaciers, so they're going to get a lot of very poorly sorted sediment being deposited in them. So they're going to, by lake standards, they're going to have a very, very weird sediment makeup. Most lakes have very, very fine silts and mud-dominated sediments. These lakes forming right next to the glaciers, on the other hand, are going to have sediments ranging from very, very fine material, clays and silts, all the way up to very, very large material, gravels, cobbles, maybe even boulders. And so that's a very clear indicator that you have to be next to a glacier to explain that kind of sediment being deposited into a lake. So within these lakes, we get layers of mud that form light and dark bands. These are called light and dark couplets, and they're referred to as varves. And the light bands represent spring and summer, and the dark bands represent the fall and winter. So the reason the dark bands are dark is because during the winter months, typically the lake will freeze over. That means the water underneath will not be being, won't be being churned up by the wind, so the lake water becomes very, very still. And so that means all the very fine sediment, the clays that have been held in suspension in the water, can rain out onto the lake floor. Clays typically have quite a dark colour to them. The other thing is that during the winter months, all the little photosynthesizing algae that are alive in the lake, well, during the winter months when things get cold, quite a few of them will die, and their bodies will sink to the bottom, and they'll also be incorporated into the sediment, and that means there's going to be more carbon in those layers of sediment. And carbon-rich sedimentary rocks also tend to have a dark colour. So that explains why you get these dark layers within these glacial lake sediments. So arguably the best example of a proglacial lake in North America are the Great Lakes. So before the last ice age, the Great Lakes was a region of relatively flat, you'd probably call it relatively lowland. It was probably a fluvial system. It's probably covered by lots and lots of large meandering rivers. So what happened was, as the ice sheet began to move over the area, it was very heavily eroded. So all the soil got stripped off, and essentially the glacier was moving over the bedrock. Now, the interesting thing about glaciers is because glaciers have weight and they're pushing down into the bedrock, they can actually cut below sea level. Okay, so if you remember from physical geology, every river, the lowest any river can cut is sea level. It can't go below sea level. Because a glacier has weight to it, it can actually push itself down into the bedrock, and so it can it can cause gouges into the continental crust that go below sea level. And so this is what the Great Lakes are. They're essentially giant gouges left by the glacier, and they've obviously filled up with water. So as the ice sheet retreated, obviously the melting ice produced large quantities of water, and that helped to fill up the Great Lakes. Obviously, the area has, since then, it's been undergoing isostatic rebound, so it's been rising up, and that's caused the water in the lakes to actually slosh around. So the water in the Great Lakes is moving around between lakes as the isostatic rebound takes place. It means, sometimes water will move more from one lake to the other, and then maybe over time it might move back from the lake it came from. This is happening over time periods of, years, decades, hundreds of years. I'm not talking on a scale of days. And so you can see it here summarized in this diagram. So this is 14,000 years ago. You can see the area is covered by the ice sheet, and the ice sheet cuts these very, very large gouges in the crust, so it digs out the lakes. As the ice sheet begins to retreat around 9,000 years ago, the meltwater fills the depressions that the glacier produced. 7,000 years ago, we actually have a short period of glacial advance. That actually squeezes some of the water back out of the Great Lakes. It displaces the water. Then we have a full glacial retreat, and obviously all that water from the melting ice comes into the lakes, and we end up with the Great Lakes pretty much as they are now. And from that point on, all that's happening is we're having isostatic rebound and adjustments, causing some water to go one way or the other, and so that's caused some slight changes in the shape of the lakes, in the last 4,000 years or so. Okay, so this is a good place to pause, so let's pause here. So get up, have a walk around, and please come back in a few minutes. So our final question is, what caused the Pleistocene glaciation? So, it's pretty obvious. Things got colder. And that makes sense. The question is, why? So, as we discussed, the most basic reason for the formation of glaciers is that more snow falls in the colder months than melts in the warmer months. So we need a net accumulation. So what we need is nice cold winters, excuse me, and relatively cool summers. We don't want too much of the snow and ice to melt during the summer months. So the most important question is how do we actually why do we achieve those conditions? And the other question is, why do they occur so rarely in geologic time? So think about it. If you go all the way back through what we've been talking about, think of the periods where we had major glaciations. We had the end of the Proterozoic, so that's around 600 to 540 million years ago. We had the Carboniferous, and then we had the Pleistocene. Those are very significant periods of time between these major glacial events. So large-scale glaciations are not common. So clearly you have to meet a very specific set of conditions to actually achieve a large-scale glaciation. So geologists, oceanographers, climatologists and other groups have tried, and they've so far failed, to produce a comprehensive model that explains many aspects of ice ages. The main problem is that the climatic change responsible for glaciations is relatively cyclical in nature, but it operates on both very, very long timescales and very, very short timescales. And each of those timescales is going to have its own controls. And the amount of variables is massive. So you have lots of things that can change the climate, on a short or long time scale, and so it makes it very difficult to work out which one of those is actually the most important. So obviously, as I mentioned, we have a few periods of mass glaciation that we've recognized, and they're separated by extensive periods of relatively warm climate. And this can be explained by changes in ocean and air circulation patterns and levels of volcanic activity related to plate tectonics. So, depending on what's going on, that will obviously that will affect global climate. So, for instance, a good example would be the Deccan Traps eruptions that occurred in India during the Cretaceous. That put huge quantities of carbon dioxide into the atmosphere, and so that would obviously have helped to increase the greenhouse effect during the Cretaceous, and so that would have helped to have kept the global climate hotter, and therefore it would have discouraged the formation of glaciers. So, that's a relatively simple, way in which, global climate could have been affected by things like volcanic activity. So, in all these situations, we have a relatively good idea to, explain what's going on. The main problem is that it's actually very, very difficult to find 100% solid data to explain why glaciation is or isn't happening. Okay, so we can say, well, yes, the Deccan Traps is clearly pumping large quantities of carbon dioxide into the atmosphere, meaning the greenhouse effect is considerably stronger, but we can't actually find the evidence from the areas that in theory could form glaciers. So we don't have the rocks from those regions, so we don't know what was going on in those regions. So we have an idea that the Deccan Traps might be affecting, the possibility of glaciations, but if we don't have the rocks from the right areas, we don't have the evidence to back that up. So that's what's going on. So that's really long-term change. These very big events, these very, very large, volcanic events associated with plate tectonic changes, the formation of mountain ranges affecting air circulations, the movement of the continents affecting ocean circulations. That's very, very big, very, very long-term variables. So then we also have to try and explain the intermediate and short-range climatic changes. And those last a few thousand years to a few 100,000 years. And that's even more difficult because there's just so many variables. However, there is one main theory that helps to explain what's going on these intermediate to short timescales. So it's called Milankovitch theory. So in the 1920s, a Serbian astronomer called Milutin Milankovitch proposed that very minor irregularities in the Earth's rotation and its orbit around the Sun could impact the amount of solar radiation that the Earth, or at least certain portions of it, would receive. So essentially, what he was saying was that there are periods of time when the Earth is going to receive less solar radiation. Therefore, that means global temperatures will be lower, and therefore you have a higher probability of a large-scale glacial event. And of course, like all good theories, it was initially ignored, but its importance was recognized in the 1970s. So Milankovitch attributed the onset of the Pleistocene Ice Age to 3 variations in the Earth's orbit. So the first one was orbital eccentricity, how circular or elliptical is the Earth's orbit around the Sun. So when the Earth's orbit around the Sun is nearly circular, then that means the northern and southern hemispheres have similar contrasts. They receive essentially the same amount of solar radiation in both the winter and the summer. So that means summer and winter conditions are remarkably similar. So that means that will mean in theory you would have warm winters and warm summers, or you would have cold winters and cold summers, depending on certain other conditions. However, when the Earth is in a more elliptical orbit, so the elliptical orbit here is marked out by the dashed line, you can see that during the most distant point over here, which is the aphelion, the Earth would receive less solar radiation, so it's further away from the Sun. So temperatures would be lower during this period here. However, as the Earth comes round and it reaches its perihelion, where it's closest to the Sun, it's going to receive a lot more solar radiation than it would do if the orbit was elliptical. So that means higher temperatures and lots of melting. So actually, when it comes down to it, if you want an ice age, the first thing you want is an orbit that's approaching circular. Because that means if you have the correct conditions, your summers are more likely to be cold and wet. So this variation works in the time frame of around 1,000 years. So essentially the process of going from a circular orbit to an elliptical orbit and back to a circular orbit is operating on a 100,000 year timescale. So essentially that means when we have interglacials, that would suggest we have a elliptical orbit. So that would mean that during the summer months, you are receiving lots and lots of solar radiation if you are essentially over here at the closest point to the sun. Whereas in the winter, you would obviously have colder conditions and you would have more snowfall. But it's because we're closer to the sun here and we're receiving a lot more solar radiation during the summer months that we're suffering very, very high rates of snow and ice loss, and so that means the glaciers can't expand. In contrast, when we have a circular orbit, you'll notice that the amount of solar radiation being received in, when the Earth is over here or over here is the same. And so that means essentially you would end up with, if you have cold winters in the northern hemisphere, it would also mean you would have cold summers in the northern hemisphere. So if that's the case, that's going to help glacier formation, because it would mean that during the summer months you would have considerably lower rates of ice and snow loss. So typically the degree of melting that occurs during the perihelion, when the Earth is closest to the sun, is most important, because that's when we actually lose material. We want the summers to be typically as cold as possible in order to avoid losing too much ice and snow. So the next variable is axial tilt. So axial tilt essentially covers the angle of the Earth's axis. So if we look at this diagram here, the white line here represents the axis of the Earth if it was perfectly upright. Okay. Now the Earth isn't actually perfectly upright. It actually rotates at an angle to this perfect north-south axis. So the angle it rotates at varies between 22.1 degrees and 24.5 degrees. So this variation is not huge, but it can have quite a significant effect on the amount of solar radiation received by the northern or southern hemispheres during the year. Now, this variation is going to work on a time period of around 41,000 years. So, if the Earth is at its maximum tilt, that's 24.5 degrees. That's going to be this yellow line here on this diagram. The poles will receive more solar radiation. So think about it. So if the sun's over here, at this point here, we have the North Pole is tilted closer to the sun, and therefore it's going to receive more solar radiation. When the tilt is lower, the orange line, the North Pole is further away from the sun, and so it will receive less solar radiation. The less solar radiation the North or South Pole receives, the better in terms of the buildup of ice and snow. So if you want an ice age, you want the Earth's axial tilt to be approaching 22 degrees. Okay, that's what you really, really want. So this actually has a relatively minor effect on global temperatures, but when it's combined with the next variable, it can actually have quite a significant effect on global temperatures, because it can lead to a decrease of up to 15% in terms of the amount of solar radiation received by the poles. So the third variable is axial precession. So this covers the Earth's wobble. So essentially the Earth actually spins like a spinning top. Okay, it doesn't spin in a nice controlled way, it actually has a wobble, so it wobbles around an axis. Now, what this means is over time, the tilt of the Earth will change. So, for instance, if we look at this diagram here, we can see that at this point, the North Pole is tilted closest to the sun if the sun's over here, and the South Pole is tilted away from the sun. Okay, so that would mean in the Northern Hemisphere, this would be summer, and in the Southern Hemisphere, this would be winter. However, every 25,000 years, the pole will shift over to here. So now the Northern Hemisphere would be pointing away from the sun, and the Southern Hemisphere would be pointing towards the sun. So that would mean the summer would then be experiencing, the Southern Hemisphere would be experiencing summer, and the Northern Hemisphere would be experiencing winter. So what this means is, if we look at this diagram here, because we have this variability over a 25,000 year time frame, this will happen. So let's just say these are the conditions now. Let's say July is summer and January is winter. Well, over time, because of this, it means eventually in about any time between about 25,000 years, it means that July will instead be winter and January will instead be summer, because the Earth's tilt will mean that conditions will be warmer during these periods. So, actually, do you know what? That's completely the wrong diagram. Oh, I'm just having a terrible lecture, guys. I do apologise. I am just not getting this right today. Let's try this again. So this diagram is showing, so at present the Earth is closest to the Sun in January. There we go. Now at this point the Northern Hemisphere is tilted away from the Sun. So the Northern Hemisphere is tilted away from the Sun in January, so it's colder. The Southern Hemisphere is pointed towards the Sun, so it's warmer. During January it's winter in the north and summer in the south. When the Earth comes around here in July, the Northern Hemisphere is pointing towards the Sun, so that means it's summertime in the north, the Southern Hemisphere is pointing away from the Sun, so that means it's winter in the south. Now, over a period of about 11,000 years, there's slight disagreement between the textbook and other sources. However, what's going to happen is over time we're going to have a precession, and so this means that in January, the Northern Hemisphere is going to be pointing towards the Sun, and the Southern Hemisphere is going to be pointing away from the Sun. So you're going to have a warm January in the Northern Hemisphere and a cold January in the Southern Hemisphere. And it also means that in 11,000 to 25,000 years' time, the Northern Hemisphere is going to have a cold July, and the Southern Hemisphere is going to have quite a warm July. So that's what the variation in the axial precession does. By changing which face essentially is tilting towards the Sun at which point, you can make summer or winter warmer or colder. So if you then combine that with the tilt, so let's say for instance you have the North Pole pointing towards the Sun during the winter months, but the tilt is relatively shallow, so around 22 degrees. So that means the North Pole is receiving less solar radiation. So that means that if we have the North Pole pointing towards the Sun, so that means summer, but the tilt is low, that means cold summers, and combine that with a circular orbit, well, all of a sudden you have the correct conditions to start forming large quantities of ice. Large quantities of ice will lead to glaciation. Now, obviously, that makes sense, I hope. So, the continuous variation in these factors causes the amount of solar radiation received at different latitudes, particularly the high latitudes, to change significantly through time. So, interestingly, the total amount of energy received by the Earth will actually change very little. However, it's all about the distribution. Is the pole receiving a lot less or a lot more solar radiation? If it receives, a lot more in the summer, there's going to be lots more melting, and therefore the glaciers can't build out. If it has, on the other hand, very cold summers, that means less melting, and so the glaciers have the chance to expand. And so, because you have these three mechanisms all working at the same time on different time scales, it means that you have a very complex, set of variables. You have these three mechanisms working, independently of each other. And then on top of that, at the same time, you have other variables like tectonic variables, climatic variables, ocean variables. Then you have the completely random events like meteorite impacts on top of that as well. And so you can see it becomes very, very difficult to actually work out exactly when and why you're actually getting an ice age being produced. So based on the Milankovitch model, the conditions we really want for glaciations are a circular orbit. In the case of if you want a glaciation in the Northern Hemisphere, we want the Northern Hemisphere to have warmer winters and cooler summers, and we want the axial tilt to be approaching 21 degrees. Those are the conditions that we really, really want if we are likely to produce a new glacial event in the Northern Hemisphere. So we currently have the orbital eccentricity and the equinoxes. So we have the orbital eccentricity, so we have option number 1, and we have option number 3 on our side. However, The tilt means the poles are receiving more solar radiation than is preferable, so it means our summers are currently too warm, and so that means the glaciers do not have the possibility of expanding. However, it would seem that additional factors, as I said, like volcanic eruptions, interstellar gases, a whole mess of possibilities, will also help to act on top of the Milankovitch cycles. So that's why large-scale glacial events are relatively rare, because you need to achieve the perfect set of conditions in order to allow them to begin. And so, obviously, when we think of short-term climatic events, they obviously work on top of the Milankovitch cycles, and those are factors like, explosive volcanic eruptions, putting large quantities of dust into the high atmosphere that will reflect solar radiation back into space, reducing global temperatures. You can have the possibility that the solar system can pass through a cloud of interstellar gas, and that would essentially mean that there would be more material, more gas in between the Earth and the Sun. That would essentially make it, it'd be like essentially the Earth and the Sun were moving through a fog. It would mean that less solar radiation would make it to the Earth, therefore global temperatures would drop. You can also have minor changes, like there could be a slight decrease in solar intensity. These decreases are very, very small, but in the right conditions, they could have an effect. And then, of course, you can have other fun stuff like happening, like a new species evolving that really, really needs to burn very, very large quantities of fossil fuel, putting tons of carbon dioxide into the atmosphere, thereby changing the greenhouse effect. So the variables are extremely huge when it comes to glacial events. So that's why they're so rare. Okay, I'm going to be honest, that was not my best presentation, for which I do apologise. It's actually quite late at night while I'm doing this. I'm not really an excuse, but some explanation as to why I'm not doing my best right now. I apologise. So don't forget, the code word for this presentation is Greenland. I repeat, Greenland. So please make sure you do the code word quiz, and keep an eye out for the next presentation.